words. What are you saying? I see lots of people writing. Did you guys have something down? I'm still looking. Okay, so we have a little bit of dissent, and I want to make sure that we're all on the same page and understanding the same thing. So I see, okay, don't erase that because I like that you have so many words written there. I didn't get a chance to read them all. There's lots of words there. Don't erase that either. Okay. I mean, don't erase your prettiness either. Did you guys have something? You same? You guys said B, C, and then A, and then D. Okay. Louis, what did you guys have written on your board? Or what are you voting for?
B equals C and D.
A and D. Okay, cool. All right. So I think that I've got still no response from there, but we'll go for it. All right. So we got two different answers up here. And friends, I really want to make sure that not just every table gets it, but that every person in here gets it. I want to make sure that you all understand this question. So we got two answers. B equals C is greater than A greater than D, and all the same. I need somebody to defend an answer. Tell me why you believe that your answer is correct.
Because accelerate.
Go. Oh, we're going to go here first, then you go second, okay?
Okay.
Sweet, go.
I said all the same.
Yeah.
Because it's acceleration and there's only one force that's acting on it, which is gravity.
Okay.
And gravity is a constant force.
Okay.
And so there's nothing else pushing the rock.
He said essentially the same thing.
He
that
did.
I was going to say.
He
but
said
in
the
much
same.
better
Yes.
words.
Okay. So acceleration is the thing we care about. So we're going to take that first. AJ, you said that there's only one force acting. What force is the force that you're saying is acting?
Gravity.
The force of gravity, but it's really the force of what on the rock? The earth on the rock, right? So if we draw a little Freebody diagram of this rock, it's got the force of the earth on the rock. It's that thing that we call gravity.
Did you say first?
Force of the earth on the rock.
So F Earth.
F Earth, yes. It looks like Firth, though. I totally understand where you're saying that. And so then you said something else, AJ. I want to make sure that I got it all. So the force of the earth on the rock, and then what? Why does that mean that they're all the same?
Because they're all being thrown down on Earth.
There's nothing else pushing or pulling. If there's nothing else
There's
pushing
no
or
jetpacks,
pushing.
there's no parachutes, there's no catapults.
Okay.
There's
Now,
no bouncy balls.
Okay.
They're not bouncy balls.
all right. Okay, so I think we're kind of, okay, so I've got that. Jay's got his hand up. Go.
It's not a free fall problem
It's not a free fall problem. Why not?
because it's being thrown downwards at an initial velocity. They all are, but at different initial velocities.
Okay, so let me ask you a question, Jay. Is that let me just to kind of clarify what you're saying. My question for you is, if these were all zero, then would you say that the accelerations were all the same?
Yes.
I'm not trying to put words in your mouth. You feel like that would be true?
Yeah.
So-
Second.
So when you ranked them, you did so by their initial velocity? Okay. So we got two
That's
different,
not by the magnitude of the acceleration.
it's like two different sides to the game here. It just got his
You're
hand
ranked
back
by
up.
velocity, not by magnitude of the acceleration. That's the problem of your thinking.
But I think that what Jay is saying is that he knows that it was ranked by velocity, but he wants to know that. But you're thinking that that's what matters, right?
Yeah.
He explained it all.
Oh, it's like you guys are like one and the same. Yeah. Yeah. Awesome. Okay, so the question to the rest of you, because we've got like 3 people that have been having this conversation. It's been a good conversation so far, but there are more than 3 of us in here. How are we feeling? Where does it fit in? I feel like there's like, you guys want to share something back there.
Oh, yeah.
Talk to me, Haley. What you got?
The only force that I can remember is that.
Okay.
Yep.
So what? So what does that allow you to argue? So there is one force. We all agree on that? The force of the earth. So I think, and Jay, you agree with that too, right? That there's just one force acting?
Oh, technically, yeah. Well, no, well, because then there'd be the rock, and then there'd be the force from the hand, like throwing it down.
But this is after it's been thrown.
After it's been thrown, yes, there's only.
So here's, I don't have a rock, but I have a frog. Okay? So I'm going to throw it down. I'm not going to throw it down that fast because then it'll be so fast you won't even be able to see it. But I'll throw it down with a little bit of velocity. Okay, so ready? Here we go. Okay? So in that case, I'm talking right after it's left my hand, so there's no contact with my hand anymore. How many forces are acting on the frog, friends? One. Now, Lizzie, you wanted to say something, or maybe not. Maybe I'm dreaming.
Oh, I said something about like the force coming. Well, no, that's not right because there is two forces because there's always two forces. You
Why?
said something about that.
Yeah?
Yeah, yesterday in my notes I remember saying that.
Didn't we have one yesterday where we had just one force?
Yeah, but
So it's two objects.
There's always two objects.
Sorry.
That's okay, and this is why we do this, right? So we can clarify things and we can get it all straight in our brains. You guys have probably figured out by now in our relationship that I'm not just going to tell you answers, right? We're going to figure them out together. So yes, there are always two something, but it's always two objects in any force interaction. Okay? And we know what those are. It's the same as it is here. The acceleration is the issue that we're trying to figure out. Let me ask you a question. Here's my frog. Here he is. Okay? I want you to watch. Let me ask first, what is his velocity before I let go? 0. We all agree there? Okay. So when I let go, I want you to watch like this little moment here, from right there to like when it gets to here. Did he accelerate from here to here, that little tiny bit? What evidence do you have that he accelerated?
It's not staying still anymore.
Not standing still anymore? Is that what you're saying? Yeah. I didn't. I just let him go. Yeah? Yeah. So it started off at rest, and then when it got here, it was moving. So if it started off at rest and it's moving now, that's changed velocity. And if it's changed velocity, it had to have accelerated. Can you tell me what the acceleration was? Negative 9.8. Yeah? Everybody happy? Okay. We're going to try something new. Nolan, you're taller than me. Come here. Ready? Can you hold this here? We gotta come back a little bit. So if you're standing back there, you can't look behind the board. Okay, this is like, it's kind of like, don't look behind the curtain or whatever. Okay, so I'm gonna start him here. Can't see him, right?
Right.
So when I let go, is he gonna be moving when he's here?
Yeah.
Yeah. Okay, so I want you to just watch this part. Ready? Here we go. 1, 2, 3. From here to here, did the frog accelerate?
Yeah.
Do you know what rate that frog accelerated at? Negative 9.81. Does that make sense? Is that okay? So we're gonna do it one more time because it's just kind of fun to watch it. Here we go. So it's gonna start a lot. Okay, there we go. Sweet. Okay, so from here down, this is like this story here, like in A, B, C, or D. Are you with me? Because it's moving down. So it's moving with a velocity downward, just like that. And I want to know the acceleration from here down. It's the same problem as I did when that board wasn't there, right? And that whole trip down, what's its acceleration? Negative 9.81. Thank you. Are you with me? Does the initial velocity matter? Let me ask it this way. What if I take the frog and I throw him in the air? As it's going up, is he accelerating? What's his acceleration? Negative 9.81. The whole darn time. Anytime that the earth is pulling on the frog and he's able to move, so he's not like landed on the floor, right? Anytime that he's able to move, he's going to be accelerating at negative 9.81 meters per second squared. We good?
Demon wing.
How are we doing? How are we doing over here? Are you guys doing okay? Yeah?
We were having a very intense discussion.
I noticed, and I kind of wanted to know what was going on, and I want to make sure you're okay. So, can you tell me what was going on? Like, what can you guys tell me? Yeah.
I brought up the point that
Yeah.
like, we were thinking about if it were throwing something down in like the initial velocity, which
Yeah,
we hit
so,
the ground
like-
first and we didn't read it
so
as
I was like,
acceleration.
Oh.
That's what
I was like-
I was trying to tell them that I figured that out. And then
I was thinking
Love
if
it.
I stood on the top of a building and I threw something down, but I also dropped something, like they would hit at the same time. I was like, no, that doesn't work.
They wouldn't
And then
hit.
he was like, no, but they're accelerating at the same time.
Bam. Does that make sense? Do you guys understand? Because a lot of you said all the same. I love this, and I love the fact that we can figure out what question was actually being answered by this. There are a lot of questions that we could answer from this information. It's just not the question that was being asked. How are we doing? Are we okay? Awesome. Okay, here we go. We're going to keep cruising. So what I need you to do is to get your notes out. We got a few notes to write down, then we'll do some more examples, okay? So notes out. Here we go, team.
God, I'm so aggressive.
Couple of friendly reminders. We've been having some great conversation about these things called forces. And we defined a bunch of stuff. And we also started drawing these things called Freebody Diagrams. Remember this? Yeah. And we drew some pictures, and we've already started talking a little bit about this. At the end of the period yesterday, I feel like we ended kind of here. Does this look familiar to you? Yeah?
Yes.
So we started talking about, in this case, the frog was just moving with one force. And is it okay for an object to just have one force acting? Sure it is. That's what happened with the frog and what happened with the rock. Here we have two forces acting, and that's okay too. Okay? Can you have more than two forces acting? I don't know. We're going to find out today. What we're going to do, I lied. You have your notes out. You guys were so good about that. I'm actually going to switch gears for just leave your notes out. Don't put them away because we're going to add some stuff to them in a minute. But I want to do something different first. Okay? What I would like you to do is to send one person from your table up to get this fancy pants gold sheet, one for each person, okay? Make that happen for me, my friends. Go grab one. You are totally going to add that to your resume.
Oh, I know.
Yes, bowling ball stopper.
Yes.
It's great. All right. So we are on the side of the gold sheet. We're on the side of the gold sheet that says FBD practice, and it's got 4 boxes. Because remember, we had a 4 and 1, right? So we're going to label them A, B, C, D. So here we go. We're going to say A, B, C, and D. And then before we get into drawing any free body diagrams or any of that kind of stuff, what I would like you to do is to write down a description, just 2 words or 3 words, okay? Maybe 1 word. Just write up next to those letters describing what happened in each of those situations. A, B, C, D. Talk to your table mates real quick. Go ahead and do that. Write down what happened in A, B, C, and D.
Moving, stop.
Wow. I mean, wow.
Marcus, is that a hand up or just a stretch? Okay.
Oh yeah, no, A is the start.
A is the push.
No, it's not. A is the push. B to C, no, B to C is the acceleration.
Oh,
Look at us.
I know, right? Sorry, I just noticed that earlier.
Oh, wait. I have a question. A was the one where it stopped.
It was just sitting there. Yes.
There you go.
Am I only circling one here?
Circle as many as you want. Yeah, yeah. All right, physicists, help me out. I need to know what happened in each of these. So I'm going to ask for your attention. We're going to start back. Let's start with Lily and Cammie. Can you guys tell me what happened in one of them? You can pick. I don't care which one you do. A, B, C, D. You pick and tell me what happened.
You push the bowling ball
In which one?
forward.
In case A, B, C, or D.
A.
In A, did I push it in A, guys?
No.
Not quite. It was B. It's okay. I'm not trying to put you on the spot. I just want to make sure that we're getting lots of participation. B is where I pushed the ball. Yep. So the ball was pushed. The reason we do this is so that we're all thinking about the same times when we're drawing our pictures, because if we don't, then it gets really jumbly really fast. All right, so there is B. I need somebody, let's see, who's got A, C, or D? Who can can tell me what happened in A, C, or D. Blythe, can you tell me what happened in one of those?
D it stopped.
D, it was stopped, right? The ball was stopped. Awesome. 2 down, 2 to go. Who's got another one? Connor, do you have one? Did you have any labels for A or C? Or can you remember what happened? That's true. I just want to know what was the ball doing? Like, what was the ball doing in A? Do you remember? It was just sitting there, right? Yeah. That's all I wanted to know. I don't need like high tech stuff. Just a description. Yep. So the ball was just sitting there. Yep. And is your hand up?
Yeah.
Cool. I didn't want to call on you if you weren't. Can you tell me what happened in
C
C?
is after the ball accelerates to like its max extent, and then it would be at a constant velocity.
Okay, so it's just we're gonna use some what was it doing?
Staying.
Rolling.
Moving, are those fair? Like you're like constant velocity, yeah, and I totally agree with that, yeah. But it was so constant velocity. It was rolling. Okay. Now this part's gonna be a little bit of a challenge, not cognitively, I hope, but from a personal restraint manner. Okay. I am going to ask you, I'm going to give you 2 minutes. And in those 2 minutes, I want you, by yourself, with your brain, you can look at your notes from yesterday, to draw a free body diagram for each of these cases. Now, before you do that, I want to tell you one thing. And that is that yesterday, remember we drew those cute little frogs? Yeah. When we do these free body diagrams from now on, though, we're not going to do so much artsy stuff. We're just going to draw a dot. And then all of the forces that are acting on the ball are going to come from that dot, okay? So all the arrows leave from that dot and go whichever direction they go. And a friendly reminder as you're thinking that through of the way that the forces need to be labeled. A force is an interaction between 2 objects. So force of blank on blank every time, okay? I'm going to give you 2 minutes. I want you to use that pencil, and I want you to draw the pictures, okay? Give it a shot. In the big boxes, yes. In the big boxes. Everybody's quiet. I will, of course, let you talk to each other in just a few moments, but right now I want you to try it by yourself. Give it a try. All right. Show me those boards. I want to see them. Got some forces on them. I love it. Looking good, you guys. I don't see tons of them. I'm still waiting on a couple. But I'm going to ask real quick as we're getting started because sometimes these are a little bit scary to draw and a little bit scary to put out there, and I want to make sure that you're feeling good. So everybody's eyes and brains are with me and up here right now. I'm seeing a lot of boards that have 2 forces on them. I think that's exactly right. What are the 2 forces? What's pushing down on the bowling ball? The earth. Yeah. So this is the time I'm going to write this down. And while I do that, I want you to make sure that on your gold sheet, which is kind of the master, that you've got this written, okay? So you've got the force of the earth on the ball. And that's another name for what? What do we call that one? FG. Yeah. You don't have to. If you have the force of the earth on the ball like this, that is sufficient for me. The opposite is not true. If you just write FG, that is not okay. That is not sufficient. Every time you draw a free body diagram, friends, I want to make sure you hear this so that you don't make mistakes later. The force of the earth on the ball is required because I need to know both objects and I need to know which one we're talking about. We're talking about the ball. Okay. Taylor, you had your board up there, right? Did you have multiple forces? What was the second force that you had acting? Floor on the ball. And which way did the floor push? Did it go up or down? I just can't see from back there. It went up, right? Yeah. So we got the force of the floor on the ball. Okay? If your free body diagram on your piece of paper doesn't look like this, fix it now. The details that I'm looking for are a dot with one arrow up and one arrow down that are about the same length. Mine aren't quite the same length, but you get the idea. Okay? And each of them is labeled F of something on ball. Okay? The force of the floor on the ball and the force of the earth on the ball. We doing okay? Okay. Once you've done that, you can erase your board. Generally, when we use boards, one person does all the writing, and that's not how this is going to roll. So I want you to erase that board, pass the board and the marker, one person to your left. And then I'd like you to have a conversation and draw a free body diagram for case B. Okay? Go ahead and do that. Need to keep cruising. We've got a lot of really nice looking boards, but I can't remember exactly what was on them. So put your boards up so I can see them. All right. I'm seeing more and more. Show me your boards. Okay. So on these boards, friends, can we take the conversations out for a second? I see a lot of forces going down. What is the force going down that a lot of you have in there? The force of the earth. And why is the force of the earth on the ball still there? It's not going away, right? It'll go away if, you go out into the middle of nowhere, in the middle of space with nothing around you. But until you do that, the force of the earth is going to be there. Friends, on almost every single free body diagram you will ever draw for me, this is going to be there, right? And where's it going to point? Down, towards the center of the earth, right? Every time we're going to write some stuff down about that in a minute. All right, show me, I see some people that have forces going up. What's the force going up? The ground, because the ground is still there as well, right? So you can call that the force of the ground, the force of the floor. Either way, it's all good. Now, I saw some other forces. Remember, a force is an interaction between two objects. What other object was the ball interacting with in part B? My hand, right? And it was pushing the ball in this direction. Would you agree? Yeah? So we're going to put another force going this direction. And this is something that I want to be very, very clear about because I had a lot of people asking. So when I was pushing the ball, I was like pushing it from this side, right? My hand was over here. So I see a lot of people that wanted to, my hand was here. So they wanted to put the force on that side where the orange hand, squiggle is, okay? Because it doesn't look like a hand very well. But you know what I'm saying. The trick is that on a free body diagram, the forces all have to come from the object. Okay, so they're always going to point from the object. So if you need to fix that on your free body diagram, on your gold sheet of paper, go ahead and do that because we're learning. This is what we do. So this is the force of the hand on the ball. You could have said the force of miscarbling on the ball. You could have said the force of the person on the ball. We can't say something like the force of the push. Because a push isn't a thing. And it has to be an object. So it has to be a hand or a ball or a hand or a person or something like that. Okay? How are we doing? We okay so far? All right, let's move on to C. Pass that board one person to the left. Erase it, pass it one person to the left, and do it. Go, go, go.
You don't know what you have.
Dimitri's turn.
Constant